All right, everyone. Oh, great. You can hear me. Cool. So yes, this is a presentation. I'm titling it "Let's Talk About Transaction Per Second." This will be very chill. Again, I think that the best way to present and to talk and give information is to have a conversation. These are all, slides that are supposed to kind of stimulate the conversation and figure out things. So if you have anything to talk about, we can definitely do that. I'll have a few slides to talk about, what is transaction per second, how we kind of get there, what the numbers mean. And then I'll do some demos too, showing very simple apps I made to just sanity check what the TPS kind of stuff you can get on Substrate and Polkadot is. And again, hopefully this will stimulate what you're thinking about, the future, all that kind of stuff. One more thing. If you've seen any of my presentations before, you might know I talk very fast. If you want me to slow down, you should just tell me, please. Just raise your hand, tell me to repeat something, no problem. But I get excited, and I just start talking very fast. So other than that, let's get started, OK? So we're going to go over TPS, an introduction to standard TPS, something new, a review of benchmarking and weights a little bit, of course, and then leading into some TPS demos. Who here hasn't heard the phrase TPS before? Yeah, I expect everyone here to know that phrase if you're in the blockchain space. Even people coming in for the first time, I think they hear this phrase all the time, transaction per second. So is it a meme, or is it a measure of scalability? I think that's one of the questions I'm going to ask. So first, I want to clarify that TPS is really from the Bitcoin era. And I think we're on, practically speaking, the third generation of blockchains. You have the Bitcoin era, you have the Ethereum era, and now we have this next generation blockchain era. TPS comes all the way back from the Bitcoin era, and it really only made sense in that era. There was only in the Bitcoin era one transaction type. It was just transferring funds. So when you wanted to measure how many times can this thing do its one thing, you have transactions per second, right? And it was used to compare different protocols. You had Bitcoin, Litecoin, maybe even Bitcoin Cash, a few other of these things that are all in this era of the Bitcoin protocol. They had different TPSs because they had different trade-offs, whether it be the size of the blocks or how frequently they made blocks or all that kind of stuff, right? The configurations. This all affected the TPS. And it really, again, only makes sense in this era. So TPS makes little sense today, right? So if we look at the current era of blockchain, we're seeing lots of different things which really muddle what a transaction actually means first, right? So first, you have transactions being bundled. You have roll-ups and account abstractions, allowing you to do multiple transactions or multiple operations in a single transaction, right? They're extremely variable. So now you have smart contract chains, right? You have a balance transfer as one transaction. You also have doing a DEX swap and a flash loan and all this kind of stuff as one transaction too, right? These things are not equal, obviously, the complexity, right? And with customizable app chains like Substrate or Cosmos SDK, transactions also, again, kind of lose meaning of what it doesn't mean to have a single transfer or a single transaction, right? And then finally, TPS, because it's been around for so long and it's such a simple number, right? You hear one number. This is the TPS of this blockchain. And you summarize all of the qualities of that blockchain with this one number. It becomes very gameable. And because it becomes gameable, it becomes meaningless, right? It really becomes meaningless that, TPS measures scalability, but it measures scalability with a bunch of decisions down the way, right? Whether you're adjusting security or decentralization, et cetera. These are all kind of factors which can affect this number. And then I have here a little picture with Godart's law. So again, when Godart's law is when a measure becomes a target, it ceases to become a good measure, right? So if we're trying to measure in this picture the number of nails made, we'll make 1,000 tiny nails. If we're trying to measure the weight of the nails made, we'll make a few very big, heavy nails. So again, when we try to make TPS be the way that we identify what is the fastest blockchain today, it loses meaning and it becomes, you end up shaping products around this number, right? Which can be bad for us. And again, what we're trying to do in this space, I would say this third generation of blockchain development is all about scalability, right? We have Bitcoin, which was the initial idea of this decentralized, consensus system. Ethereum introduced the idea of a Turing-complete computer to it. Now we're trying to see how fast can we make this? How can we make a computer that can satisfy the needs of a world of Web3 applications, right? And so when we think about, okay, the only number we care about is this TPS number, which is, arguably scalability, we end up sacrificing a lot on security and decentralization, which are very key parts of, a Web3 application. We want all of these things, but the reason why this is such a hard triangle to satisfy is because usually you're sacrificing one to get the other, right? So again, TPS is not a great metric, but it is something that's being used around, right? So
I just want to mention, I ran through this article when just trying to get some of my words correct and just searching around what the latest talk about TPS. It's funny, this was actually just made 6 days ago. So there's actually a pretty good article here, you should check it out. And it talks about TPS, again, being kind of a very old, flawed metric. I think we can all agree on that, right? So what are some better measurements we can use to measure scalability? Well, one I'm going to introduce is this standard transaction per second. So let's not, back in the Bitcoin era, TPS meant something. It meant a balance transfer between two accounts, right? I think a balance transfer is still a really great vanilla metric for blockchains, because all blockchains generally have a cryptocurrency. At some point in their, in the logic, they need to support transferring their cryptocurrency, right? It may not be the main purpose of the chain. Like Polkadot's main purpose is not to be a cryptocurrency, but it's it's a functionality which I think is you can use as a sane vanilla metric, right? But what's important is we need to standardize what and how we measure that metric. So in this case, we are introducing this idea of a standard transaction per second. You might see this a little around the Polkadot ecosystem and on the forum and stuff like that. And the idea is that this is supposed to represent some kind of reproducible, cross-chain, cross-ecosystem standard, which we can get a sanity check. Now, I would say this. STPS can also be gamed. This should not be, again, a single number which represents the whole blockchain, but at least can give you a sanity idea of okay, how well can this function as a cryptocurrency blockchain, right? And that's fine. So in this context, a STPS is a keep alive balance transfer. That means a balance transfer from an account where I'm not transferring all my balance. For example, you might have a blockchain where when my account goes to 0, it does a bunch of cleanup, right? A bunch of operations. We're going to ignore that. We want to just transfer that my account's still alive, but I'm transferring. Also, that I'm transferring to an account that already exists, right? So on a blockchain, you might imagine that if you create a new account, there might be a bunch of setup stuff and a bunch of overhead. We don't want that either. We just want to measure from one existing account to another existing account, a simple balance transfer, right? And then, of course, we want to assume worst-case scenarios for this transfer, right? We don't want to have someone be building all this optimistic and caching layers and storage layers and if you transfer exactly 1.25 that we go down this path of simple no, we want to assume all the worst case scenarios. So you have the things like the account not being pre-cached in storage. Storage is a very expensive part of any blockchain, where the transactions are not being optimistically parallelized, right? You can't assume that every transaction will be non-colliding, right? So you can only parallelize transactions in a single core or in a single synchronous block when there's no interaction or intersection between database entries, right? Some blockchains have this as an optimistic case, but obviously, if we measure things in the optimistic case, in the real world where people want to attack blockchains, it's not going to be a very useful metric, right? And of course, we want it where the data is accessible by light client. So, one of the things that we really believe in the Polkadot ecosystem is the future of light clients, is the future of having, these trustless systems available to end users when they actually use the products. And so, putting things into a Merkle tree, that's heavy, right? If you have all of this optimistic storage stuff where you use all their non-light client supported database systems, you get more performance, but then you lose out on decentralization and trust freeness, right? So these are some of the basics of kind of things we want to see in the STPS, right? And again, I think a pretty fair assumption is that we assume in this case that all blockchains fundamentally manage a cryptocurrency. So, high level. Anything not clear about this so far? Good. Okay, so that's one metric. Yeah, quick thing in the front. Can we get the mic for you, or maybe I can repeat your question as well.
What is more expensive for the keep alive or?
Yeah. So what is more expensive between keep alive and not keep alive? The keep alive is cheaper, because we don't assume, so we know, because it's keep alive, the account will not kill itself when it's transferred. So that weight will be slightly lower. And that's actually why in Polkadot we have both transfer and transfer keep alive. We give you the option to know that there's a cheaper transfer if you want it, right? Okay. Another kind of metric, which is probably better, and again, that could be in addition to STPS, but makes more sense for our current era of blockchain, is some kind of weight / gas / computation per second, right? Some kind of high-level measurement of how many operations can this blockchain do, right? So this is a more general metric where we assume blockchains are not just tools for cryptocurrency, but are a basis for building Web3 applications, right? General VMs. This can account for variability in block time and differences in transaction complexity, right? So even if your block time was really fast or really slow, how many kind of computational operations you can do per second is a consistent metric. And this is very much similar to what you expect with CPU chips, right? Like you have AMD and Intel, you use gigahertz, right? That's a very easy metric to determine, okay, how fast does this thing run? We assume in this case the blockchain platforms provide Turing completeness, right? Obviously, we don't want to have a subsystem which only does certain things. And of course, a metric like this, again, is very dependent on the VM used, right? So, and VMs will themselves have different trade-offs, right? So, we use right now WASM. We're looking into RISC-V. People have built their own VM systems, whether it be like Move or the Solana VM or the EVM or whatever, right? All of them have their own different trade-offs, right? So it's going to be, even in this context, hard to measure everyone with just one number, right? But I think this is the kind of direction we should go towards, way better than STPS, right? And if we can come up with great kinds of like simple computational problems to test on these different VMs, I think we can come up with a really nice kind of high-level metric for all these systems, right? Yeah, and all I want to mention here as well, just because you have a VM with a really high STPS, or in this case, gas computation per second, it could be that it's designed in a way that makes it really hard to be flexible or makes it really hard to develop on. There's a lot of factors into what makes a product successful, right? But again, this is a reasonable metric, at least better than the normal TPS. Finally, outside of the blockchain, we need to also start considering resource consumption per transaction. And this is really something to think about in terms of like what you're seeing with ZK rollups, right? Like on the actual blockchain, you're verifying one ZK proof, and that could have in it hundreds, thousands, even millions of transactions, because you can even recursively nest these rollups, right? But the time it takes to actually generate that proof, that ZK proof, is a lot of work, a lot of computation, a lot of resources. Now, on the blockchain, it can verify it quite quickly. That's an amazing property. But we can't just then say this blockchain is super fast and super cheap and has high TPS. In this context, we need to take into account that fact that there was some work required and resource required beforehand to actually set that up, right? So I think we also need to start thinking about the costs of the hardware used, the cost and time to take to prepare a block to actually go through, right? For Polkadot, that's not really a problem, but if we transition to more roll-up-based scenarios, or again, as more roll-ups are actually being out there, we can't just take the single TPS metric as this is the number, right? We have to also take into account how much time did it take to prepare that block. Okay. And finally, always in context, right? So these metrics, as soon as we've made a metric, it becomes gameable. It becomes useless, right? So we always have to have these metrics in context of what it means and the decisions and trade-offs they make. Of course, I can pick bigger hardware. I can pick faster computer. I can pick, less nodes, right? Less validators, closer connections in the network. All of these things are choices you can make. But are they actually good, especially in the Web3 context? Are you still providing a resilient system, a secure system, a decentralized system, open, public, permissionless, censorship-resistant, borderless, right? Are all these things still applying to get your number, right? So every number should have a big asterisk, and you need to really understand deeply this technology stack. So again, what I really want to say is that these numbers can be manipulated, and I'll show you how I can manipulate them here in the demos, okay? So any comments about what we've talked about so far? Can we agree that maybe these other metrics are slightly better? Again, still probably gameable, but I think way better than what we have today with normal TPS, right? Great. So, Polkadot TPS. How should we evaluate the scalability of Polkadot? I think that's a very relevant question for all of us here, right? Our goal is for the Polkadot relay chain to have 0 transactions per second. Does this resonate with you guys? We do not want transactions on the relay chain. This is not the goal. Our goal is, Polkadot, it scales through sharding. We have all these different execution cores. We shard execution, we shard data off to other parachains. The relay chain itself should have no transactions. It should entirely be used, all of its computation, all of its resources, to secure and provide the Polkadot network, this sharded ecosystem. So our goal on Polkadot is to have 0 TPS. Right? I think it's very funny all the time I see, these random crypto metric sites, and they have Polkadot there with a TPS number, like how many transactions or user transactions are coming into Polkadot. And it's totally useless. Polkadot is not meant to be a place where you're doing DeFi trades, you're doing all these kinds of individual user transactions. It's meant to be a hub for securing other parachains. The actual volume of scalability of Polkadot is the sum of all different parachains, all of their transactions, all of the applications on those going through, right? So again, Polkadot scales through execution data sharding. The relay chain itself is not expected to have many. So then the question we're really asking is, how can we scale one of these individual cores, right? I also want to mention, we have a lot of thought about how we continue to make Polkadot more flexible and scale to the needs of different applications. So let's assume, again, if you were I guess you might hear maybe later with one of Gav's presentations or in his previous talks about core jam, core time, if we assume that Polkadot can provide like 330 cores, right? And that each of these cores can process around 3,000 standard TPS, right? And then with the introduction of these flexible, like agile core time and core jam, which will allow us much more, agile and flexible access to these different cores, you can imagine that Polkadot is going to provide a lot of flexibility to scale these applications, right? This STPS number. You can imagine that on a single core, you can have 10 or more applications running all that single core, each with 33 transactions per second, or STPS on their little core, right? Because that is supported. That's the amount of resource available on a single core. You can also then go on the other side of the spectrum and have a single application access all of the cores of Polkadot at once, right? And produce a single giant block, right, with 1 million STPS in it. A single block with 1 million STPS, right? This is exactly the kind of vision that we have with the introduction of things like core time, core jam. And this is the kind of way that we expect to scale not Polkadot, the relay chain, but the applications built on Polkadot. You can achieve 1 million STPS with the advantages of sharding this execution, with what the designs and the features we're building with Polkadot and the future of Polkadot. And again, what's nice is that the way we've designed Polkadot, and we are designing Polkadot to be, is that this can be dynamically decided per block, right? As you have resources, and as you need it, you can access these cores agilely and flexibly, right? Cool. So now we're going to start going towards more demo side and talk about a little bit more of the away from the ideas and go into some more tangible content, right? So how do we actually measure throughput in the Polkadot ecosystem? All right, who here is not familiar with weight? Great, yeah, this is the developer conference. I think everyone here should have heard this before. Weight. So what is weight? Weight is a general concept, a high-level concept, used to track the consumption of limited blockchain resources. So blockchains are really these small computers with very limited resources. How much memory they have, how much computation they can do per block, how much storage they access, all that kind of stuff. They're very small machines. It's very much like building for an embedded system, right? And weight is this idea to try to measure and capture how much resources a single block or a blockchain can use, right? In Substrate, you might know that there's just two main limiting factors right now. We have execution time. How much time does it take to execute some logic? And the size of the data required to create a Merkle proof for that data, right? And this second one, this POV, this proof size, is important for parachains, because this is how parachains get validated in the Polkadot ecosystem, right? That we are able to provide a proof of the storage being manipulated. We provide a block, which is the executed data. We have Polkadot validate that this is valid, and then run it. So these combination of limiting factors are kind of the things we need to be able to make Polkadot work. And I want to note that we started off with weight not having this proof size, but then once we started launching parachains, we needed it. And I could expect in the future we could add other items to weight. So I can imagine right now it's only 2 items. We could, for example, introduce things like memory, stack size, etc. Right? There might be other things that we need to include in the future of Polkadot to actually measure what the limiting factors are, right? But for this presentation, we're mostly going to focus on the execution time, okay? It's the one that kind of makes the most sense. It's most relatable to other blockchains. In this context, we have in execution time, 10 to the 12 weight is 1 second, or 1,000 weight is 1 nanosecond, okay? And this is how we measure all the different pieces of our Polkadot ecosystem. Now, to make weight meaningful in the context of a decentralized network, we have to have some assumptions. So we have to assume some kind of recommended hardware. So when you run a validator in the Polkadot ecosystem, there is a minimum hardware you have to run. Again, you have to remember that, like right now, I'm running an M3 Max. Before I had a M1, this computer is faster. So how long it takes for me to execute some logic will be faster on this computer than my other computer, right? Or another computer that you have or any computer in the system. Every computer is slightly different. Even between M3 Maxes, the differences in the manufacturing or whatever, the heat of my computer, us being in Thailand, like that all can affect the performance of the hardware, right? So we need to, when we actually do benchmarking, we find the weights, assume some minimum hardware, right? And do a lot of averaging. We also want to assume the worst case scenario. Our goal is not to find the most optimal TPS we can find. Our goal is to find the TPS or the weight which keeps our blockchain safe, right? Our goal as blockchain developers is to keep our blockchain safe from attackers. After that, we want to optimize performance. But we do not want to optimize performance sacrificing safety, right? So we always assume worst case scenario, because we always assume every actor in our system is an attacker. And of course, we measure the block import time. Why do we measure block imports? Well, when we consider attacks in the network, what we really care about is not the performance of someone building a block. That's a single person building a block. What we care about is all the other nodes who have to import that block. So imagine if I wanted to attack the network, what I would do, and again, there was no weight, there was no benchmarking, I would produce a block that is huge, super heavy. It's valid, but it takes, let's say, 5 seconds to execute, where we expect 2 seconds. And I give that to everyone. And now everyone on the network is spending 5 seconds to import this block, and the next block producer, who's supposed to build a block after me, missed their block slot because they were importing my block. Right? We don't care, again, the performance of a single node. You can build a super fast computer. What we care about is that everyone has a minimum hardware, and that within the bounds of what the weight of the block is, you're able to import that block within a certain amount of time, right? So block import is the key attack metric for the network. Okay? Is everyone following so far? Feels good? Okay, good. I'm getting there. Okay, so what does the block import look like? So on Polkadot, we have 6-second blocks, right? And we actually allocate 2 seconds of that for import. The other 2 seconds is for networking latency, and the other 2 seconds is for execution, actually building the block, right? But 2 seconds are there for block imports, and in that block import, you have to do a bunch of stuff. You have to, have some general overhead for block imports. Then you do some on-initialized logic, the extrinsics you want to run, some on-finalized logic. And again, the extrinsics themselves, there's a bunch of extrinsic base, like how much it takes to actually set up an extrinsic, and then the cost of the extrinsic logic itself, right? So this is kind of what's happening. All of this, everything we have to do to make the block work and imports has to happen in this 2-second window, okay? And if you want to look, all of these block weights are available in the constants of your blockchain. So you actually go into the runtime, you can configure them, but if you want to just see what the weights are for different chains, you can see that. So you can see here, I don't know how big it is for you all to see here, but the max block, the ref time here, is 2 with 12 zeros. That's 2 seconds. That's our maximum execution time or import time for a block, right? Here's proof size, that other part. You can see even here how much a base extrinsic costs. So every extrinsic takes 124 microseconds just to process, independent of the actual logic of the extrinsic, right? And other stuff like that. So you can see all these details here in the block weights. And as we mentioned, again, transactions in these systems of these flexible app chains don't make any sense, because I have here 3 different transactions, completely different weights, right? So you have a remark, which is basically like a no-op. It basically does nothing. Here, you have the weight of a remark is, of course, the base weight plus 0.3 microseconds here, basically nothing. A basic transfer, you can see here, half the weight of a transfer is the base weight, half the weight is the actual transfer logic. And you have things like voting in the conviction voting system. In our current OpenGov system is way bigger, right? So how can I measure what a TPS of Polkadot is? I'll just use this one, right? This is way better, but it's not actually that useful, right? So again, it's all manipulable. You need to get in the context of what we're actually doing and what we're actually measuring here, right? In this context, execution time or execution throughput is way more relevant of a metric, right, for our kind of blockchain. Okay, great. So from there, I'm going to actually start a quick demo, and I'll show you a little bit of my setup. So I want to mention here, this demo is not complex, intentionally. A real benchmark, I'll make this bigger, of course. A real benchmarking for our ecosystem requires launching multiple nodes, having them be on different parts of the of the world, right? So they have network latency, having them connect to a parachain or relay chain, spamming it, like that kind of stuff. That's not the point of this presentation. The presentation is supposed to show you some basic tools, and know that we have some tools that actually do full network benchmarking, and that we are still making tools which account for things like asynchronous backing and all the other optimizations we're making for Polkadot in the future, right? But this is going to be a basic demo showing you some basic numbers, how we can manipulate them, how we can see them, okay? So you can learn from this, but don't treat this as like, this is the number I saw from Shawn, this is what Polkadot can do, right? Okay, great. So I have this repo. I can share it with you all, maybe in one of our chats or something, like a Telegram after. You can find it here, Polkadot SDK TPS Workshop. It's on my GitHub. And you can see here I have a couple folders. So I have different kinds of nodes. I'll talk about that as I go through my presentation more. I have here a meter. This is a simple JS app which meters the transactions per second on a block. And I have a spammer. I have a spammer with a bunch of different scripts to spam. So let's start. Let's actually go here. Oh. Why did it change? No. Let's go. So sad. I had it all nice and organized. Okay. So let me start a standard node. Okay. And actually, you'll see here, I have the start node script. So when I'm running, so here a standard node, this is exactly a duplicate of the substrate node template. No changes, nothing. I'm just running it. And here, if you look at start node, actually I have some commands. So two things I'm doing here. Let's look at the second command first. The first thing I'm doing here is I'm saving my, my blockchain to a special folder, the database, because I will actually use it later to actually do some more benchmarking. I'll show you that. I'm using ParityDB, not RocksDB, because ParityDB is faster. And then I'm increasing some limits. So I'm making sure that our transaction pool can support, hundreds of thousands of transactions. Our pool supports, megabytes of data in it, so we're not limiting that either. And that we have a transaction band second of 0. So basically, I'm kind of setting my node in a way that I can spam it and it's not going to yell at me. Obviously, if you're running a node in the ecosystem, you do not want to accept spam. You don't want to accept someone flooding your node because they're trying to probably DOS you, right? In this context, I want to get DOSed, right? I want to be able to see what my full throughput is, right? So I have these configurations. And then every time I run it, I purge a chain before I start a new one, okay? So here, I have a blockchain running. Then I have the meter. So let's do yarn start on the meter. And you can see, basically, it listens to my blockchain and tells me, okay, block 7 had 1 extrinsic. That's the set timestamp extrinsic. That's the one that's always there. And basically has 0 pending in the transaction pool, right? So let's do our first spam. So let's do here, so node, let's do real-time, what's the options? Real-time TKA. In this case, TKA stands for a transfer not killing account. Transfer keep alive. Transfer keep alive, okay? So this transfer keep alive script, you can see it's running. You can see my blockchain is starting to get transactions. You can see here, is everyone able to read? Is it big enough? Yeah? You can see here that block 11 had 3,800 transactions. Block 12 had 6,500, 6,500, and then 3,000. So you can see here, this is probably our, our saturation here. We're getting to 75% of a full block, and we're getting a TPS of around 1,100 transactions per second, okay? Let's do one more. Let's do right here a remark. So I mentioned here already that the transfer keep alive is a, quite a big one. A remark is much smaller, so I should be able to get more in there. So let's do remark. And I'll show these scripts as well. There's a lot of things I want to show here. Please feel free to ask any questions here. This is where, we're doing live coding. We can see stuff. But let's run this real quick. So it's spamming my node real time with transactions. I'm getting here 16,000 or 1,600 transactions per second with a block fullness of only 64%. That's less, right? So let's take a quick look at these scripts that I'm running, just so you can get an idea of what I've done here. And we're going to make these things better. We're going to get more transactions as we go through. So this was real-time remark and real-time transfer killing. So what I mean by real-time here is that I am, in real time, signing a transaction, sending it to the blockchain. Signing a transaction, sending it to the blockchain, right? And you see it's very simple. I have here Alice and Bob. I have here one dot. I query what Alice's nonce is. I get her starting nonce. And I'm manually incrementing the nonce, right? This is important because if you ask for the nonce, it doesn't take into account the transaction pool, right? I think Polkadot.js has some tools that can do this, but this is the easiest thing to do. You just get the current nonce, you increment it yourself, and I have here a loop which basically takes a transfer to Bob for 1 unit and signs and sends it. That's how I'm getting this throughput, right? And with remark, I get the same. So a couple things I want to myself remark on. What's interesting here is I'm getting saturation, but I'm stuck at 75%. And here in the remark, I get saturation, but I'm stuck at around 60%, 64%. Does anyone want to guess why I'm not achieving 100% saturation? Yeah. Okay, so you're saying that the node does not allow transactions when the API, JSAP. No, actually, that's not true. It's not that. One in the back. Can we get maybe the mic to the back? Or you can scream and I can repeat that's fine. Yes, there are runtime block weight configs. Exactly, that is exactly correct. So in this context, there are some configurations which are actually limiting how much I can actually use. Okay, let me skip this real quick. I'll go back to that. This is what I want to show first. That the normal default breakdown of a block is we only allow actually 75% of the weight of a block to be used for regular extrinsics. This is important because in the case where your blockchain is getting spammed, and there's some really important things that need to happen. For example, let's say a governance proposal to make sure the chain doesn't die, You do not want that some NFT transaction is blocking some very important weight or some important upgrade or whatever, right? So we allocate here a 25%, which on most blocks don't get used, but is there to allow for these really important transactions to happen. Who here, without naming names, can think about a chain which didn't do this, and their chain went down because they were getting spammed with NFT transactions? Right? We've had this in the beginning. We know again, we're not optimizing for TPS. We're optimizing for safety, right? That a safe blockchain allows for this buffer of transactions here, right? This isn't going to make our blockchain have the highest number, but it's going to make our blockchain resilient, right? When you have in mind just a TPS number, you just put everything you want. So that's one thing I want to put in that context, okay? One more tool I want to show you. This is my previous slides here, that we can actually verify how long it takes to import this block. So in this context, again, I'm running a blockchain on my computer. My computer is not the standard hardware, right? And the weight system is maybe not perfect. Benchmarking could be overestimating, which I'm showing here it does. So we can actually go through and import the blocks of the past. So let's go back to my demo. Let's stop the node. Remember that in my configuration here, I set that I'm going to have the node save its database to this temp folder, right? So what I can actually do is I can then go back and using tools inside of Substrate, actually import a specific set of blocks and see how long it takes to import those blocks, okay? So let's go here. So let's go back to my node. Let's go back to this thing here. So on blocks 7 through 15, I was doing the first benchmark. That was the transfers. So let's go here. Let's take this command. Ooh, that's not what I want to do. Okay, I have it saved somewhere else. Ooh, sorry, I'm just live stuff. Okay, let's go here. So I have the commands here, other commands. Let's take this command and put it here into the node. So what I'm going to do is I'm going to benchmark my blocks from, and it was from which blocks? It was from like 10 to 17, right? From 10 to 17. And you can see here I'm pointing to the database where I have my blocks. So now you can see here it's rerunning the block imports and telling me how much time it takes to actually execute that block compared to what the weight reports it tells me. So let's take a look here. So here we have a block 12 with 6,500 transactions used, but we're only using 57% of its reported weight. So I want to show here. We report that this block takes 1.5 seconds, right? That was the 75% we saw. 75% block weight, 1.5 seconds, we reported this block takes. But when we imported this block on my computer, it only took 0.8 seconds to import the block, which means that we're overestimating the weight for my computer by 2x, right? 50%. Does it make sense what I'm showing you here? Right? Now, this is, again, a sanity check kind of showing you that, again, this weight here is not representative of how long it takes. It's representative of how long it takes on standard hardware, a minimum amount. As long as we can import it faster than the reported weight, we're good. We're safe, right? That's what we want. So let's go back to my presentation real quick. Where's my presentation? Here we go. So in general, Substrate always overestimates weights, right? And this is important because the worst case scenario, it always overestimates. In general, the worst case scenario is not the average scenario. In most cases, we overestimate and you lose performance because of that. But we have no other better way to empirically measure this data while maintaining worst case scenarios. And again, most of the time it's not worst case scenarios, but whenever there's an attack to your chain, it will be a worst case scenario, right? So we always want to measure and have things be in this worst case overestimate, right? And so one of the goals and continued goals of benchmarking is how can we bring down the overestimation while maintaining the safety? But in general, we are always overestimating. So even the TPS numbers I'll show you today, probably we can do better if we sacrifice some of the ideals we have about making a safe, resilient blockchain. And I want to mention here, my computer is fast. So obviously, I'm going to say that we're overestimating a lot because my computer is quite faster than the standard hardware. One of the decisions we made in the Polkadot ecosystem is to not have hardware, which is a supercomputer, right? Some other blockchains, we won't name names, they want their hardware to be this, like, thousands of dollars per month, day, whatever, to run. We want our system to mostly run on standard hardware. I think as a general idea of where Polkadot wants to be, we always want to have like a current generation gaming computer level of hardware. We think that's something that's accessible by most people around the world, especially if you want to run a validator, and that's a nice level of decentralization while also having performance. But you can see, again, my MacBook, my brand new one, is quite faster than what you actually need to run a validator, okay? And again, you can also run this on your computer. So if you want to know how fast your computer is compared to the standard hardware, you can run this command, cargo run release. So this is any substrate node, the benchmark subcommand, and then machine. And this will basically run machine benchmarks and show you a percentage compared to that standard hardware, right? That's what this output will be. It'll show you, again, 170%, 190%, et cetera, of the standard hardware. Okay.
Can I have a question?
Yes, please, a question.
So you explained why we can actually use 75% of the block space.
Yes.
That's fine. But what about the remark one? We could achieve 60%.
Perfect. That's a great demo. So I'll show you the. That's actually I have a demo for that. Thank you for reminding me about that. So in the case of the remark where we were only able to achieve 65%, there's some other bottleneck, right? So let's actually run my node again. This bottleneck I have from just kind of testing things around is from actually the transaction pool, right? So there's actually a better way we can actually submit transactions, and this is called basically pre-signing. So in this context, I'm sorry, I'm jumping two things here. The limit in this case is not the transaction pool, it is signing the messages. So because we are running a loop and we're signing messages one by one, the actual signing process is quite heavy. So if we want to actually achieve the full throughput on this standard node, let's run here a pre-signed. So let's do yarn start the meter, and let's do node pre-signed remark. I believe with this, I'll be able to actually achieve the full throughput. And again, what I'm doing here, as you can see here, I'm pre-signing a bunch of extrinsics, incrementing the nonce, right? And then submitting it all at once. So I'm not actually lagging behind on terms of just me literally doing cryptographic signing. It's actually quite expensive to do it. And so this is kind of funny to see that once you get to the remark, that kind of number of transactions, this is actually the bottleneck. So here we're doing pre-signing. Let's see if we get 75%. Let it think. There we go. Now we got 75%, right? So that's the difference. So that's the first bottleneck is actually signing the messages. So you always, when you want to build a TPS or a spammer, pre-sign the messages. Thank you. Great. Okay, so let's go now. What I wanted to show next was, okay, I had just shown you that we don't use all the block weight. Let's pump the numbers, right? Let's actually start a new blockchain where we actually use 100% of the full block weight, right? So let's switch from standard node to full block node. Okay, let's run that. And let's get some new numbers real quick. Let that run. Any other questions while we're waiting? Yeah, so full block node, thank you. So let's look at that, let's look at the code base. That's a great question. Here, again, the standard node, which I said was just an exact copy and paste of the substrate node template. The full block node is just changing one thing. If I go to the full block node, I go into the runtime, I go into the source, the lib. Here I mark things with workshop. I've changed here the normal dispatch ratio, which is normally, where is that? Here, or sorry, I'm blocking it with this thing, which is normally here 75. That's the normal 75%. I just changed to 100. This, again, everything inside of Substrate is configurable. So I just basically say, I want to use 100% of my 2 seconds for execution, right? I will get another 25% additional bandwidth from this, right? And again, there's a lot of configuration stuff you can do here. This is the block weight here. So all that stuff here can be configured here and adjusted. Like your block time, your execution time, all that stuff can be adjusted, right? So this, again, with TPS numbers, you can kind of play with whatever you want in these blockchains, right? They're not really real numbers. But let's get to the full block. And let's, in this case, on the actual full block node, I want to show a few things. One, let's see here. If I go back to my history, the full block node is probably the best representation of a real blockchain in the Polkadot ecosystem. What I did actually, in addition to this, was I actually generated a bunch of accounts ahead of time. I basically funded them with balances. So if I go here inside of the full block node, inside of the node source chain spec, you can see here I made this new function, pre-fund accounts. I picked number 10,000. And here I generate all of the same, where's the pre-fund accounts? FN pre-fund, yeah, here. I generate all of the same accounts as normal, but then I also go through and generate Alice accounts and Bob accounts with a special prefix, right? So these are individual accounts, and I give them money to. And this will allow me to measure the STPS, right? Again, STPS is from one funded account to another funded account, everyone being different, right? So in this context, let's actually run the STPS benchmark. So that's running. This is running a new node. Let's run the meter. Yeah, there we go. The meter's running. OK. And then let's run node STPS. And we'll take a look at what this little code is doing. OK? So let's go here, back here while it's running in the background. I will go to the spammer STPS. So here, again, a very simple, script. First thing I do is I go ahead and I generate a bunch of accounts using the same prefix as I made inside of my node, right? And I'm storing the accounts and the nonce of Alice inside of some array. And I'm also getting the accounts for Bob and putting that also in an array. So I know who's going to send to who, right? And then I go ahead and I pre-sign the transactions. So every transaction will be from Alice to Bob. So Alice 1 will send to Bob 1. Alice 2 will send to Bob 2. Every account is different. Every receiving account is different. And I pre-sign all these transactions, and I increment her nonce. And then at the very end, I actually go through, and I submit all those extrinsics to the blockchain, right? So if we go back to the spammer, it's still, see, this is quite a bit slower in this context, because, again, generating these keys is quite slow, even on the JS side, also on the Rust side. So again, this is something that I didn't want to show too many demos of this, because it takes a while, but let's let it run and build up these accounts. And then it will sign all the messages, then send it. What else do I want to note here? I only chose 10,000 accounts. There will be some repeats here. So I think I'm actually spamming how many transactions? 2,500, right? So in this context, across all the transactions, there will be some repeats accounts, but within one block, you won't have any. So I think it'll still be safe here. But probably for a real benchmark, you want to increase all these numbers and have it be way longer, right? But then it will also be a bit slower, okay? Let's go. Let's see. How's it going? 90%. So now it built all the transactions, and now it's spamming it. Bam. Look at that. Full. 99%. This is a absolute 100% full block. I'm using 100% of the block weight. I guess one transfer doesn't fit 0.009 of a weight, right? But you can see here I'm getting a full block at around 1,457 transactions per second, okay? And I want to show you something like this. So this is a basic number. This is kind of where we're at with Substrate. And if you look, let's go back to Firefox. We have a tweet from Gavin Wood on June 8th, 2020, which says basically the same number, right? Now this test was set up a little bit differently. This was actually tested on a multi-node network with, again, with a 3-second block time using the STPS thing. It was actually this repo over here by Nikolai. It's this sub-bench random, again, quite old repo. But this basic number of what we're achieving makes sense. Again, if you do the basic math, you have a transfer has a certain weight. A block has an available amount of weight. If you divide the two numbers, you should get a number around 1,500. And we were able to show on a decentralized network, we were able to achieve the same number, right? So in this context, I'm trying to say to you that networking and the and propagation and stuff like that has not been a bottleneck to our TPS in terms of computation, right? Or in terms of what we're doing here. So even though I'm running these benchmarks on one computer, I know that based on these other benchmarks that we're not actually getting limited by the networking. So one computer test is actually kind of reasonable at this point, right? Okay. How can we go further? Let's go back to my presentation. Oops, sorry, that's not what I want. Slideshow. Okay, so what we can do even further now, we have a full block node. We can then create other nodes. We can change other parameters. So we can have here a super node, which instead of only having 2 seconds for block import, has 4 seconds, right? We can make a fast node, which instead of 6-second blocks, has 3-second blocks, right? All this is very easy to configure. I think I'm just going to show you how I configured that. I might not actually run the benchmarks right now. So if we go here, back to my repo, if I go to the super node, and I go into the runtime, into the source, the lib, and I go to workshop, you can see here, I can just change this execution time to 4, right? Add some more weight to my thing. Now I'll have 4 times 10 to the 12 weight available in a block, right? Similarly, if I go to fast node, let's go here, the runtime, the source, the lib, I can go here, I can change the milliseconds per block from 6,000 to 3,000 milliseconds per block, right? And all these things, again, will adjust and change what the TPS will be. In this context, I have the same amount of weight available, but my block time is half, so my TPS will double, right? In the other case as well, I have more weight, TPS will basically double. I can adjust all these numbers and change this TPS to whatever I want. That's, again, trying to show you that these numbers don't really make a lot of sense. Yeah. So another thing we can do to improve and push our throughput is transaction batching, right? So we can reduce the per extrinsic weight by having all these extrinsics or all these transactions happen in one extrinsic and use things like batch to actually wrap it all together, right? This will also reduce the overhead on the transaction pool. The transaction pool needs to manage thousands of transactions. If instead we can make a couple of transactions, a couple hundred, with a whole bunch of transfers inside of them, it's way easier, right? Now, is this cheating? The answer is kind of yes from me, but if we're honest, this is exactly what all the other chains are doing. Like, Ethereum is touting that account abstractions is going to bump them up to like 100,000 transactions per second. Rollups are basically batching. Like, all the other ecosystems are basically measuring themselves in all of these super optimal batch scenarios. We can do it too, right? So I want to show one more demo. So I'm going to run a fast node. Okay, let's go here. I'm going to run my fast node. CD fast node, and let's start this node. And then I'm going to run a batch transaction on it and show how I can just get crazy numbers. I can push it to whatever I want, pretty much. So it's building. I'm going to run the meter, yarn start, and then I'll show you really quickly here. Let's actually do the batch. Let's do batch, right? I have transfers. Let's do batch transfers. That's probably an interesting one. Is it running? The node is still thinking. We'll pause real quick. OK, good. It's running. Let me just run this real quick. Permission denied. No, I need to do node batch TKA. OK, let's let this run real quick. It's quite fast because, again, the number of transactions I have to make is much slower. And let's look at what the numbers we're going to get are. So in this context, I'm batching 100 transfers per transaction. So here, I only have 55 transactions per second in my block, but times that by 100, because there's actually 100 transfers happening in each one. So here, I'm achieving, again, only 89% of the block fullness, but I'm achieving like 5,000 transactions per second, right? Now, let's look at remark. Remark is even crazier. Let's go real quick here. Let's spam remark, and then I'll show you remark. Because the transaction is much smaller, I can actually batch 1,000 per transaction, right? So let's see what kind of numbers we're actually going to get here. I think actually my JS, I couldn't figure it out. My JS app is kind of messed up. It actually says infinity at some point because I think it's processing so much stuff. Let's see what the numbers we actually get are. 1 second here. So that's 44% full with 43. That's 43 times 1,000. So 43,000 transactions per second. Fullness here 47. Yeah, so this is like 47,000 transactions per second. No, here, this is at 94. 94,000 transactions per second if you consider remarks, if you consider batching. 94,000, right? Like these are the numbers that people like, they're touting over in these other blockchains. We can do it too, but it's just all bullshit. It's all bullshit numbers, right? That's what I'm trying to say. So let's go back here. Here are some of my results, all in one slide. You can see here I have a standard node doing transfer keep alive, remarks, pre-signed remarks, the STPS, etc. For standard, full, super node, fast node, I'm getting numbers like 83,000 transactions per second, if you're measuring it that way. If you're measuring, again, just actual balance transfers are more useful, still I'm getting 5,000, 6,000 transactions per second. Like, these are great numbers to have. But we're making sacrifices. We're making adjustments that make it. And again, what I'm trying to say here is that when you go out there and someone says, hey, we can do 10,000 transactions per second or whatever, how do they do it? I'm showing you here from the beginning, I can start with 1,000 in the most basic way. I can get all the way to 83,000 if I change some things around, manipulate exactly. So everything here is kind of being changed and modified. For my tests, the limitations currently are the transaction pool, like ordering, so you don't want to have a lot of transactions in the pool. Deep client code, like I couldn't even find all the things I need to still investigate, but like there's deep client code which is trying to limit and keep the blockchain safe, which I'm hitting into certain limits. Overestimated weights, more efficient logic for balances and basic extrinsic, and other general optimizations. My future hope is that we will actually have a development sprint in the Polkadot SDK to actually optimize for throughput. I would love to have like a week or a month where we just basically, how can we optimize this number and just do everything we need to the client to actually make it better, right? Things with async backing, etc. We want to actually create reproducible benchmarks for Polkadot and parachains, right? Better tooling, better education, etc. Right? So I think I'm basically at my limit, but I'm around. I'll take questions. Maybe one question before we go. Yeah, you have someone. Observation, please. Here, take the mic, please.
Hello. Yeah, the substrate benchmarking framework. I've done testing with it, and
Yes.
I've noticed that storage reads and writes. They're the weights that are generated.
Yes.
Each storage read and write, you have a dB weight.
Yes.
That's added to that. But the ref time for the actual benchmark is also including the actual reads and writes. So you're almost including it twice. If you use your benchmark on on transactions that are heavy on reads and writes, you'll get a much bigger difference. But if you do transactions that are primarily computation, then you get closer to the expected.
Yeah, so that basically what's happening here is that that's a kind of a historical thing. I think I talked about this in some of my other talks about benchmarking, but the high level idea is that database is a heavy part of the process, and we weren't able to get reproducible benchmarks measuring the database along with the execution logic. So we separated the two. There is a little bit of overhead caused by that. Again, I think that you're actually identifying a place we could improve our benchmarking further to minimize that overhead, but right now we are double counting some database stuff. Yeah. It's just to keep things safe. Again, what we don't want to do is we don't want to make up a number. We have a system which is like reproducible and has good results. If we can make a system which is better, that's great, right? So anyway, if you go around and people ask what the TPS of Polkadot is, say 83,000, and then show them this presentation, okay? Cool, thank you.
We have time for two more questions.
Great, I love it.
We have time.
Yeah, any more questions, any more comments?
Please be fast.
Yeah, so when the execution scales, we are increasingly bottlenecked by networking, though. And the networking doesn't realize, like, from one side of the world to other side of the world with the full bandwidth that you buy from your ISP. So I think networking will be a big bottleneck. And again, a lot of these benchmark tests are all happening on small networks in these optimal conditions. One of the notes I make is that we all use the same hardware in the world. We all use the same internet. We all use the same hardware. We all use the same software, right? If someone is having an order of magnitude better performance, they're probably cheating or changing in some way, right? It's not like that you can just achieve faster access to the internet, right? You know, I think Polkadot is measuring things quite fairly. I think that this is a pretty good pulse for what we can achieve in the ecosystem. So when Radix 2?
When what?
Radix 2.
Radix 2, oh, the binary tree. Yeah, I mean, that's another optimization as well. There's so much we can do. Again, I think a mindset of going and actually doing a sprint where we optimize specifically TPS number, even though it's not, again, it's not a real number. I want to mention, I don't support TPS, but people in the world seem to care, and so we should just care, right? We should just do a little bit of work to make it happen. But yeah, I would hope soon. I hope soon. One more question.
Okay, you briefly mentioned that VM also matters a lot. So how do we tackle this problem in measuring weights? So
exactly. So I'll tell you this: when I joined Parity, the WASM VM we used was 10 times slower than the native. That's why we had this WASM and native compilation, right? Nowadays, our WASM is so much better. It's about 1.2, 1.3 times slower. That's pretty okay. And that's why we're able to get rid of native. That's what we're trying to get rid of, right? But things like, we're now benchmarking RISC-V. People have their own VMs. The EVM has its own weight limits, all that kind of stuff. So when we do benchmarking, we are always benchmarking using our real system. So we're actually benchmarking using the WASM interpreter or the WASM compiler that we have. We're actually running the exact code and measuring it empirically how long it takes to run. And we're doing lots and lots of benchmarks, averaging it all out and getting a number. And it's been pretty consistent. It's not deterministic, it's consistent. Does that make sense?
Yeah, thanks.
Yeah. Cool. Again, I can keep going?
No.
Oh, sorry.
No,
No.
but it was excellent. Thank you.
Yeah, great. So again, I'm around. If any of you are interested in this stuff, I think this is a great place people can contribute. And they can contribute quite easily here because this is not the kind of stuff that needs to be heavily audited or affects the runtime very much, right? Benchmarking is something that you can bring and pull to Polkadot with your own ideas, with your own optimizations, your own performance things. And generally speaking, those kinds of PRs are much easier to review than, let's say, making a new palette, making a new runtime change, that kind of stuff, right? So if you're interested in this kind of stuff, there's a lot of room for improvement, right? There's a lot of room for clarity. And I hope that we will bring that to the Polkadot ecosystem, okay? Great, thank you.
Okay, thank you, Shawn. It was excellent.